The equation of conservation of mass, or continuity principle, is a fundamental principle in engineering mechanics, including in fluid mechanics. Mass cannot be created nor destroyed. Mass can only be stored or transported. Thus, the rate of change of mass in a control volume is equal to the difference of mass influx into the control volume minus the mass flux out of the control volume. This is shown here in a symbolic form with m, the mass of the control volume, and small m with a dot above being the mass flux in and out of the control volume. The mass flux is equal to the integration of the density of the fluid times the velocity component normal to the cross-section, integration over the cross-section area. A key parameter is the cross-sectional average velocity, V bar, defined as the ratio of the volume flux divided by the cross-section area, definition shown here. The equation of conservation of mass can also be presented in a differential form for a small control volume, dx, dy, dz, shown here with ρ, the density of the fluid, and vx, vy, vz, the velocity component in the x, y, and z directions. This can also be expressed mathematically in a vector notation, shown here, with the variation with time of the density, plus the divergent of the product of the density by the velocity vector, being equal to 0. For an incompressible fluid, the density of the fluid is a constant, and the equation of conservation of mass can be simplified in the form of a conservation of volume, in which Q, BQ is the volume flux or discharge. Let us look at a few applications. First, let us consider a pipe junction for a water utility pipe network as sketched below. Water is incompressible, and the equation of conservation of mass gives Q1 equal Q2 plus Q3 with the sign convention shown in the sketch. Another application is a discharge, Q, a volume discharge, Q, of an incompressible fluid in a circular pipe of diameter d, in which the velocity distribution is axis symmetrical and follow a power law, with Vmax, the maximum velocity on the pipe center line, and small r, the radial distance from the pipe center line. The equation of conservation of mass gives a relationship between the cross-sectional average velocity, V bar, the maximum velocity, V max, and the power law exponent, 1 over n. For a circular, smooth pipe with n equals 7, we obtain that the maximum velocity, Vmax, is 1.2 times the mean velocity, V bar. A further application is a fully developed open channel flow in a wide rectangular channel, for example, a river in flood, as shown here, the Brisbane River in 2022. The velocity distribution in a turbulent flow in an open channel follow a power law, shown here, in which y is the distance normal to the invert and d is the water depth. The integration of the equation of conservation of mass give a relationship between the cross-sectional average velocity and the maximum velocity. And in an open channel with n equals 6, very typical, we obtain Vmax equal 1.17 times V bar. The equation of conservation of mass is possibly the most fundamental principle in fluid mechanics, including its application and use in physical and numerical modeling of fluid flow. This is further discussed in a number of relevant YouTube video movies in the same channel.